Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Are you ready with a pen and paper to learn the topic for today? We are discussing variation of molar conductivity for strong and weak electrolytes with change in concentration, or what is also called as dilution of the solution. What happens to molar conductivity of each of them when you dilute the solution further? Pen and paper so that you have your notes ready and handy for future reference. Now, in order to understand this topic, we've got this data for you. Now, if you notice in this particular chart, we've got three columns. The first one depicts concentration in moles per liter. We are measuring the molar conductivity of different electrolytes at different concentrations. So, we start with 0.1 leading to 0.05, 0.01, 0.005 and so on, leading us up to infinite dilution. That means a solution which is very dilute, so that further dilution does not show any variation in its molar conductivity. To make things simpler, I have taken examples of two electrolytes over here, a strong electrolyte, example KCl, and a weak electrolyte, example acetic acid, and we have tabulated the molar conductivity of these two electrolytes at different concentrations. Please remember, you are not required to learn this table at all. I have tabulated this table to make things easier for you to understand. Because if you look at this chart, there are many things that we will be able to decipher. Let's start with the first one. You see the concentration at 0.1. That means when we are talking about compared to 0.0005, this will be a higher concentration, right? So, at a certain concentration, the molar conductivity of KCl is much higher than that of acetic acid. Acetic acid is an example of a weak electrolyte. We dilute, concentration decreases. The molar conductivity of KCl shows a slight increase. Go on, 0.01, the molar conductivity increases further. Now, if you compare the increase in molar conductivity of KCl, so it's 141 minus, let's say 141 minus 129. So, the conductivity increases by just 11.3. On the other hand, for acetic acid, the molar conductivity becomes almost 3 times. Go on further. The molar conductivity is increasing in small steps as we keep diluting the solution till it reaches a limiting value of 149.9. That means beyond this there is no increase in the molar conductivity. Come to acetic acid. Now here what happens is at every stage, if you notice, there is almost 3 times increase in the molar conductivity of acetic acid. And there is a very large increase when we change from 0.0005 or 5 into 10 to the power minus 4 moles per liter to infinite dilution. That means there's a very high increase. These points, let us tabulate them. This is just to show you how we can make interpretations from the mathematical data which we obtain by experiments. Now, here again, I have placed the chart here in front of you and we've got the points written for the strong and the weak electrolytes. So, we are going to generalize some points. Molar conductivity at higher concentration of strong electrolytes is greater than that for weak electrolytes. We are not saying that it is very high. What we are saying is Out of the two, strong electrolytes have higher molar conductivity as compared to the weak electrolytes. That becomes our first point. Second point, molar conductivity of strong electrolytes increases on dilution. Yes, it increases on dilution for weak electrolytes as well. You can simultaneously have a look at the chart as well. The third one, for strong electrolytes, the increase is not substantial and a limiting value is reached, which we call as molar conductivity at infinite dilution, represented as, how do you represent it? Yes, we represent it as lambda with a small naught sign above it, or at certain places we also find it as lambda with an infinity sign at the top of it. What does infinite dilution means? A solution which is so dilute that further dilution does not cause a change in molar conductivity. Are we able to reach this limiting value in the case of weak electrolytes? No, it is not so in the case of weak electrolytes. Let us see why it is so, why we are observing these changes. We take the example of again sodium chloride as a strong electrolyte. Now we've got NaCl. NaCl is made up of oppositely charged ions. It's an ionic compound. In solution, the ions separate out as Na positive and Cl negative. Of course, they are hydrated ions, but for the sake of simplicity, we are going to simply maybe write it as aqueous here, right? Now, sodium chloride aqueous solution changes to Na positive aqueous and chloride ions aqueous. With the result, what has happened is, in the case of an aqueous solution or when dissolved, the sodium and the chloride ions separate. When I have got a solution of sodium chloride, now here the sodium chloride in a smaller volume, the ions of sodium and chloride are quite closely packed. On dilution, what change takes place? We've got a bigger volume of the solution, so let's make a little bigger vessel. Due to dilution, the ions, of course, the degree of ionization increases, but only to a slight extent. We say degree of dissociation because ions are already there. So the ions simply separate out further on dilution. They move away from each other. So what dilution is doing is, of course, it is helping to increase the number of ions to a small extent, but at the same time it is helping to move the ions away from each other, thus causing an increase in molar conductivity. What happens in the case of weak electrolytes? Now, in the case of weak electrolytes, why do we call them weak is because they are only partially ionized. So, in an aqueous solution, a molecule of acetic acid will actually ionize to form acetate ions and hydrogen ions, right? So, there is an equilibrium, that is why we put this sign, there is an equilibrium between the molecules and the ions. When we start adding water to it, the equilibrium starts shifting towards the right till a stage is reached when complete ionization has taken place. So, when you are adding water, one, there is ionization which is happening, and at the same time there is separation of the ions which will happen due to the effect of dilution, right? this explains the difference, their difference in behavior on dilution. Why? There is a small change in molar conductivity for a strong electrolyte, whereas there is a large increase in the molar conductivity of a weak electrolyte on dilution. Would you like to note down these differences? So here again I have tabulated it for you. So we have got the first column showing the variation, or explaining more appropriately, the variation in the conductivity of a molar conductivity of a strong electrolyte and that of a weak electrolyte. So in the case of a strong electrolyte, it is already completely dissociated in solution, and there is only a very small increase on dissociation on dilution. Whereas at higher concentration, the forces of attraction, the inter-ionic forces of attraction are reduced, and at higher concentration these forces of attraction are very high, whereas on dilution these inter-ionic forces are reduced and these ions are free to move about, causing an increase in molar conductivity. Weak electrolytes, they are partially ionized at low concentration. So on dilution the degree of dissociation is increasing as well as the distance between the ions, causing a much greater increase in the molar conductivity at higher dilution. So now we have discussed the behavior of strong and weak electrolytes. We have this table, right, which we've done earlier. Now based on this table we are going to plot the graph, that is we are going to represent the variation of molar conductivity of strong and weak electrolytes against under root of C, square root of the concentration. Why square root of concentration is that it has been observed that the molar conductivity of strong electrolytes varies directly as the square root of the concentration of the solution. So when we plot the graph pertaining to this data, what do we have? Now when we are plotting the graph, there are certain important points that I would like to point out over here. Always remember to mark what you are depicting on the x and the y axis. These are points to be remembered when drawing a graph. Make sure that you represent the unit, you write the unit of the physical quantity which you are representing on the y axis and the x axis. So molar conductivity here is Siemens centimeter square per mole, whereas on the x axis, because we have taken under root of concentration, so we will have under root of its unit as well. So moles per liter square root or mole per liter to the power of half. Third, you have to be careful that you are taking the distances, equal distances on the x axis or y axis depending upon the scale. So 0.2 is the difference here, 0.2 is the difference here, 200, 200. Now in many books you will find, or in many texts you will find that these scales are different. You could also represent it as 50, 100, 150, 200, 250, 300 and so on. So accordingly the height at which your graph is being formed will also change. So supposing I take it as 50, 100, 150 and then 200, so my graph for KCl will start somewhere over here. So don't get confused, be careful to note the values that have been taken on the x and the y axis. Now if you observe the graph over here, yes, I have made it a little bit cleaner for us to be able to read it. Now see the graph for KCl, potassium chloride, again a representative of a strong electrolyte. The graph is almost a straight line, and if I extend this line backwards, what is called as extrapolation, it will give me the value of the molar conductivity of KCl at what concentration? At zero concentration. Zero concentration means infinite dilution. So the point where the graph cuts the y-axis becomes the molar conductivity at infinite dilution. Look at the graph for acetic acid. Now here if you notice, with the dilution the molar conductivity is increasing. Now initially there is a small increase, and then towards infinite dilution we notice that our graph goes parallel, almost parallel to the y-axis. So it is difficult to obtain molar conductivity at infinite dilution by just extrapolating this particular graph. So how do we determine the molar conductivity at infinite dilution for weak electrolytes? That's something interesting, right? So again, comparing the strong and weak electrolytes vis-a-vis when we study it graphically. For your reference, I have kept the graph on the side. So graphically, what do we observe? For a strong electrolyte, the graph is a straight line. No, it is not so. For a weak electrolyte, it is a curve. Molar conductivity directly varies as the square root of concentration at higher dilution for a strong electrolyte. No, it is not so for a weak electrolyte. Molar conductivity at infinite dilution can be determined by extrapolating the graph to zero concentration. No, we cannot do that because our graph becomes almost parallel to the y-axis at infinite dilution. Now, how does the graph help us to determine molar conductivity at infinite dilution? This expression lambda m is equals to lambda m infinite minus a root c was given by Kohlrausch. At some places it is also referred to as the Debye-Huckel-Onsager equation. You can follow whatever is defined by your curriculum. Now on the y-axis we have represented lambda m, right, plus mx c. Now if you remember the slope intercept formula that you do in mathematics, y is equals to mx plus c, where we have c, that is the y-intercept representing lambda m infinite. That means where this particular graph cuts the y-axis, that point represents the molar conductivity at infinite dilution. The slope of this graph m will give us the value of minus a. And what is minus a? It's the Kohlrausch constant. X is the term or the variable which we are taking on the x-axis. So here it is under root of c. What are the factors on which a depends? It depends upon the nature of the solvent, the temperature at which the molar conductivity is being measured, the type of electrolyte. What do we mean by the type of electrolyte? We mean by the nature of the charges being carried by the cation to the anion. So when I have a salt or an electrolyte of the example NaCl, Now the charge on the cation and the anion is 1:1, right? So this type of an electrolyte is called as 1:1. Let's take the example of CaCl2. Now here the charge on the cation is 2 positive, whereas the charge on the anion, each anion, is negative. Hence this type of an electrolyte is 2:1. If we take the example of calcium sulfate, CaSO4, so the charge on the cation 2 positive, charge on the anion 2 negative. This type of an electrolyte is 2:2. Two electrolytes of the same type. So let us suppose I am comparing calcium sulfate and magnesium sulfate. Their value here, because both of them are 2:2 electrolytes, their value of A, the constant, the Kohlrausch constant, will be the same, and this can be used to determine the molar conductivity. Now we've done the molar conductivity of a strong electrolyte at infinite dilution. We've seen that weak electrolytes, on the other hand, we are not able to determine the molar conductivity by extrapolation, right? So how do we determine their molar conductivity? At infinite dilution, how do we determine for weak electrolytes? That's a big question, right? We are going to answer this question in the next video, where we shall be discussing the Kohlrausch law. So look forward to this video and stay subscribed. See you soon.